as the title says, it's a survey talk on quantum algorithms for computing class groups. And so it is a combination of quantum computing and number theory. So keeping balance between these two things is not going to be easy. I'm trying my best to keep the balance, but I'm pretty sure that at some point during the talk, all of you will feel that the material I'm presenting is easy, and I'll do my best, and we'll see how it goes. But let me give you an overview of what I'm going to talk about today. So the first thing is, of course, stating the problem. And once you have seen the problem clearly, then some classical results we will list. And the reason I want to state the problem is that I'm pretty sure that everybody knows that what's the problem. But the point is that I want to make sure that I've already talked about input and output, because I'm insisting on output for a different reason. So, and we will take a look at the list of classical results. And once I list them, I'll give you a general idea of how, a brief idea of how the state of the art in the classical sense works. There are two reasons. It's interesting to know how it works. But the other reason is that even the quantum algorithm we want to see at the end of the day is very closely following the same ideas, except for the fact that giving this exponential speedups for some parts of it. Once we are done with seeing classical results, then I will review some related quantum algorithms by listing them. And when I say related, they are not all for solving class group problem, but they're related to number theory. And the ideas for the one we want to talk about is somehow generalized during the time from those ones. For example, in the list of those algorithms, you'll see one for solving Pell's equation or unit group computation and stuff like this. But it will be quick. And then, of course, as we are going to talk about quantum computing, I need to briefly talk about that. I cannot be too detailed on that. And a lot of information are there to discuss, but I'm just going to talk about the things we really want and we really need to present the result we are interested in. So I'll be very quick on that as well. But my goal is to give you the flavor of quantum computing in this part of my talk. And later, we will turn our attention into the hidden subgroup problem. And what is that? I will clearly state that later. But the point is that why are we interested in that? Because this appears at some part of our algorithm. So basically, we will reduce class group computation at some point to hidden subgroup problem. And this problem is very well known in quantum computing because there are many other algorithms which use hidden subgroup problem in the heart of them. So it appears in the heart of many more quantum algorithms. And for that reason, I'll specifically talk about them separately. And then you'll see some related results on how we can solve different cases of hidden subgroup problems. And finally, we turn our attention into a polynomial-time quantum algorithm, which was introduced by Biasse and Song in 2016, which solves class group problem. It also solves a principal ideal problem, and probably you can use it for other purposes, such as solving norm equation or computing Ray class groups. But I'm going to focus on the part which is relevant to the class group problem. OK, so it's time for definitions. And well, very simple stuff that you probably already know these things, but I just want to have a recall. So let K be a number field, and we're dealing with the ring of integers of K. And we say two fractional ideals I and J are equivalent if they satisfy such equation where alpha is an element of K star. And this the set of equivalence classes is called the class group. And the point is that you can also define class group for any other order in K, not necessarily the ring of integers. But the reason I worked with this definition is that it's simple to state here. If you want to work for the orders, you can consider all invertible fractional ideals and then mod them out by principal ones. And as soon as you know this is a group, then the question is, do we know anything about the structure of the group? And there is a well-known result that says that for any number field K, the class group is actually a finite abelian group. And the cardinality of that is called the class number. And well, it's obvious that we know a lot about finite abelian groups. So the question is, once you know it is a finite abelian group, what is the structure of the group? So this is the story of the class group problem. And this is a very well-known problem in computational algebraic number theory. And I don't think we really need to present some motivation for doing such thing, because it's very interesting and known for a long time and have been worked on for a long time enough. But if you want to know, then there are applications of these class groups in cryptography and post-quantum cryptography, homomorphic encryptions, and some other things. So, but what is the problem? So I insist that I will tell you what is the input and output. And for us, an input is a number field k and of degree n, which is usually to a computer is given by a polynomial, no matter if you're dealing with a classical computer, quantum computer. It's given usually by a polynomial, which is irreducible of degree n. And then you see your field as a quotient ring. And what is the output? So the output is a structure of the ideal class group. The reason I'm trying to state the output clearly is the fact that later on you see that in many of these algorithms, almost all of them, we will assume that there is we have access to a generating set of the class group. So if this is the case and you have access to a generating set for the class group, one might ask, okay, if you have a generating set, what are you looking for? So the point is we are looking not for a generating set. The structure of the group is our goal. And usually we want to give some invariant factors or stuff like that to show the structure of the group. Okay, now let's go and see some classical results. So the oldest one comes from Shank's paper from 1969. This is exactly the paper that he introduced, baby step, giant step method, which is used since then in various problems, and it's a very cool idea. It also solves the. It also gave a solution to discrete log problem, and in that paper he also works on imaginary quadratic number fields and computation of class groups for them. But he doesn't address complexity analysis of that. Later, in 1982, independently, Lenstra and Schof worked on the complexity analysis of the same algorithm, and assuming generalized Riemann hypothesis, which we will assume here as well, they showed that the cost is exponential in terms of the log of discriminant. I should point out that when I'm talking about complexities, I usually consider log of the things. And for example, here I'm talking about log of the discriminant. If you want to see that it will be polynomial in terms of the discriminant, but we do care about the log of the discriminant. So having that in hand, then Hafner and McCurley in 1989 introduced an algorithm which works on imaginary quadratic number fields. And again, the cost was sub-exponential in terms of the log of the discriminant. And note that the degree is fixed here. And later on, 1990, Bookman gave an algorithm which works for a fixed degree number field. And again, it is sub-exponential in terms of, so it works for higher degrees of number fields, but the degree should be fixed. And then it will become sub-exponential in terms of the log of the discriminant. And if you really want to release the degree over there, then it will become exponential, actually. So it took a while so that we can see a result which releases the degree. And this happened in 2014 by Biasse and Ficker. They gave an algorithm which works on arbitrary degree number fields. And this time it is sub-exponential in terms of log of the discriminant and the degree of the extension. So this is the state of the art for classical algorithms. And most of these, sub-exponential algorithms more or less are following the same pattern, and one is generalizing the other one. And I'll present the idea of these results, how they work in general. I won't present details in that, but since it is relevant to the quantum algorithm we are going to talk about, so we want to take a look at what are those ideas behind the algorithm. So it's more or less following the ideas in for a as in we do that in number field C. And the first step is to choose a factor base B. What do we want from this factor base? We want to make sure that this guy generates the class group, the classes of these guys generate the class group. And this is this can be a set of all prime ideals so that they satisfy norm bound. And of course, we want to make sure that they generate the class group. And what are these norm bounds we are looking for? There are two norm bounds. One of them is this Minkowski's bound. And if you really use this, your algorithm will be unconditional. But the point is that if you use that, the sad news is that unfortunately, you won't be able to end up with something better than exponential. So your algorithm will become exponential if you use Minkowski's bound to get the factor base. And but the point is that if you assume GRH by a theorem proven by Bach in 1990, he provided a norm bound. And using that norm bound, what you can do, you can generate, you can actually get B in polynomial. You can actually have B, which is of the size of polynomial in terms of the discriminant. And it's not really trivial to say how it works, but you can, based on this norm, you can have an algorithm which produces B in polynomial time. So, but then you have to assume GRH. And for our purposes, we will assume GRH to get the algorithm which works in quantum computing. Okay, I'll state the norm later when I get back to the quantum algorithm. But for now, we'll think B as somehow being possible to be computed in polynomial time. Now, the next step, once you have a base factor, is collecting relations. What is this about? So basically, when you have your B, it's a bunch of ideals, and then you can have a surjective map phi. How does it work? It sends E1 to En. It maps it to the product of classes of PIs to EI. So this is the map, and this is surjective map. So looking at the map, it tells you that the class group should be isomorphic to Z to the N mod the kernel of the map. So the only question we have at this point is, do you know what is the kernel? Can you compute the kernel? Because if you know the kernel, you know everything. So the goal here at this step is to collect relation which helps in computing the kernel at the end of the day. So what type of relations are you trying to collect here? So how does the kernel look like? You should be able to find relations of this type. So if the product is equal to a principal ideal, then you're good. So we are looking for such relations. But the hard part is exactly here. None of the algorithms I was talking about in the previous slide will give you an algorithm which can compute, which can find these relations in polynomial time so that you have enough of these, and then you can get the class group. So you will get a bunch of these relations using any of those algorithms, but you are not sure if you have enough of these relations. So basically, the dominant term for the cost of the computing class group is for this step, collecting relations. But once you are done with collecting relations with potentially enough relations, then the rest is just linear algebra. So you form a matrix where for each row you will consider one of these guys X, and then in the rows of that in the row relevant to X, you will put EIs, and that's a matrix. If you want to just know class number, compute a Hermite normal form, which is not costly. And if you want to know the structure, you compute the Smith normal form to give you invariant factors. Eventually, after this step, which is not really that costly, then you have a potential group which you think you might be the class group. And the reason it is not exactly a class group is the previous step. Now, at this point, you can do a verification. So luckily, we have access to class number formula and stuff like this. And we know that whatever we have got from the previous step, the class group will be a quotient of that. So the only thing you have to check is the size. And this verification step uses class number formulas to check that. But I don't want to get into details of this because I just want to present the idea and tell you that how it works in general, and to tell you the fact that basically the quantum algorithm we are going to talk about is going to give you a speed up on this step. And it will be exponential speed up to make sure that we can compute these relations efficiently. And that's all what I wanted to say about these classical ones. Now let's take a look at some quantum algorithms. So the first one I want to talk about is the one given by Halgren in 2003 that solves Pell's equation. So this is a polynomial time algorithm, so you can efficiently solve Pell's equation while in a quantum world. And later on, Hallgren gave another paper which introduces algorithms for computing unit group and class group for a fixed degree number field. And so it is basically polynomial in terms of the discriminant of the field, and it is an efficient algorithm for such computation. And later on, well, of course, at the same time, Schmidt and Vollmer in 2005, and I think they both presented both these results were presented at the same conference. They solved unit group problem and class group problem at the same time, and well, the costs were both efficient. Then later on in 2014, Eisentrager, Hallgren, Kitaev, and Song used ideas from previous works of Hallgren to be able to release the degree for computing the unit group. So we have an efficient quantum algorithm to compute unit group for arbitrary degree number fields. And the reason I've written that in red is that the next paper is the one we are interested in, but the ideas are all borrowed from here and generalized from this paper. So, and the state of the art for this computation is actually given by Biasse and Song in 2016. And they introduce algorithms for computing principal ideal problem and class group problem for arbitrary degree. So, and it is efficient, works in polynomial time. For this one, for class group problem, it works in polynomial time in terms of the degree of the extension and the log of the discriminant. And in case of the principal ideal problem, it works in polynomial times in terms of the degree, the log of the discriminant, and the norm of the given ideal.
Armin, in analyzing the complexity of the quantum algorithms, do you need to assume Riemann hypothesis or not?
This one I'm talking about, yes, we do need. I'll tell you where exactly we need. And this is not coming from the quantum side of it. It is coming from the classical side of it, where you really need to have, first of all, you need a generating set for your class group. And if you want, you can use Minkowski's bound, but you won't end up with a polynomial.
Well, I mean, if you assume Riemann hypothesis, you can get representatives for each class within the square of the log of the discriminant, right?
Yeah. Yeah. So, but if you want to get it in polynomial time, you need GRH.
That's right, because without, I mean, if you don't assume Riemann hypothesis, the bound will be some power of the discriminant.
Yes. Yeah. Okay. So, so this is the paper. This is the result I'm going to talk about will be this class group problem, and from this paper. But the ideas are coming from this, so I might get back to this at some points and mention some stuff. And by the way, this is not a complete list of algorithms you can find for quantum algorithms doing some number theory work or number theory works on number theoretical problem. I just mentioned the ones that I thought were related. There are other lists that covers more maybe. Okay, so but let me summarize the algorithm of Biasse and Song from 2016, how it works. It exactly follows the ideas from the paper by Eisentrager, Hallgren, Kitaev, and Song, which just works on units, but this one works for a class group problem. And how does it work? So the problem of class group problem will be reduced classically to computing S units. I'll mention that I'll clearly define these things later. This is just an overview. I want to give you an idea how we want to proceed. And both S units and continuous hidden subgroup problem will be introduced officially later. But the idea is to reduce class group problem to computing S units. But this part is classical. This is exactly the part that we had for classical algorithms. And then for computing S units, we have a quantum reduction to continuous hidden subgroup problem, which I'll introduce later. But this part is quantum, and this is the main contribution of the authors of the paper for this problem. And once you turn the problem into an instance of continuous hidden subgroup problem, then you can apply an algorithm from Eisentrager, Hallgren, Kitaev, Song 2014, which efficiently in polynomial time solves this continuous hidden subgroup problem. And actually, the continuous hidden subgroup problem is defined by these people so that they can solve it efficiently. And it is a variation of the hidden subgroup problem, which I will talk about both of them. Okay, once we know what we want to do, let's talk about a quantum computer, as this involves some quantum computing. But there are many things comes to mind when you hear about quantum computer. The first question is this: what is a quantum computer? So simply, I can tell you a quantum computer is a computer which works based on quantum mechanics. And what is the history behind that? Well, a long time ago, it was around 1930, a physicist noticed that classical mechanics cannot really explain some of the phenomena they're dealing with, and they noticed that they need another model. And they eventually ended up with having something called quantum mechanics for explaining those things they couldn't explain previously. Once they had this quantum mechanics in hand, then later on we had computers as well. And then the question was, okay, simulate some of these stuff and see how it goes. But the simulation was quite hard or impossible in some cases, as they were trying to do stuff that was not good enough. And they noticed that, okay, a classical computer apparently is not a good thing enough to simulate quantum mechanics phenomena. And well, a few scientists suggested, including Yuri Manin and Feynman, suggested that how about having a computer which works based on quantum mechanics so that we can simulate our quantum mechanics phenomena. So that was the idea behind that, and this happened around 70s, I believe. And once the idea was out, people was wondering, right, okay, if you can make a computer in classical sense, why not making a computer which uses other sort of modern physics theories? And then the next question was, during the 80s, people were asking, okay, having such computers in hand, what kind of questions will you give it to so that they can solve? Because they already knew that some of the problems are not good to be implemented in a classical computer, but will be potentially good in a quantum computer. So the search was going on. But before getting there, let me ask the next trivial question, because we have heard that quantum computers will give you exponential speedups and you will get algorithms which run much faster in comparison to classical algorithms. So is it really a supercomputer we are talking about? And the answer is simply no. It's not a supercomputer, and it is not a replacement for a classical computer. By classical computer, I mean the computers we are using today. So it is not a replacement, honestly. This is a different technology. It also does computations, but this is not a replacement for this. As if you want to use a quantum computer when you have a large scale one at hand, you want to use it for everyday work such as streaming or, I don't know, web browsing, it's probably slower than a computer we are using today. The reason is that the cost of these basic operations on a quantum computer is likely to be more in comparison to a classical computer. So why are we bothering? There are various reasons that we are bothering, because first of all, we know that there are problems that we can solve more efficiently using quantum computer. When this happened, the first instance was given by a very important case was given, but maybe it's not first, Simon's problem was there. But anyways, Shor's algorithm for factoring integers was introduced in 1994. And people noticed that, okay, now we have a polynomial time algorithm for factoring integers if you want to use a quantum computer, while the best known one in the classical sense is sub-exponential one. And even after 30 years, we still are in the same place. Sub-exponential is the best we can get in a classical computer. So there were results that showed that if you have a quantum computer, then you are in better situation for doing computation, at least for some problems. And the other fact was that, well, there are physical constraints for improving our classical computers today. So to some extent, you can improve your memories and stuff like this. But eventually, physicists think that maybe it's not enough at some day. I don't know exact answer to that. But anyways, it's good to have a backup for our computers. Well, it's not going to replace them, but if you want to do computations in some way better, then you can use other devices as well. But before getting into details of quantum computing a little bit, let me state the other thing which is important here. So the next question is, what type of problems get benefit from quantum computing? So if you go back when we were having these computers, classical computers, smaller so that they can fit on a desk, then the question was, what are the problems we can really solve with them efficiently? So can we solve all problems that can be modeled for a computer? And around the 70s, probably people had the guess that no, we cannot solve all of them efficiently, at least at the time. And well, one of the cases, at least we know that is not solvable efficiently, is like traveler's salesman problem. But then if you cannot solve a problem efficiently, sorry. If you cannot solve a problem efficiently, the question is, if I give you a solution to one of those problems, and you can you verify that efficiently? And the answer was yes. For example, for a traveler salesman, you cannot solve it efficiently, but if I give you a solution, you can verify the solution efficiently. So the next question was obvious. If I can check a solution in efficient way in a computer, can I solve the problem, the same problem, in an efficient way? And this became a very important problem, and formally stated as P versus MP. And this was stated in early 70s by Cook. And it's probably the most important open problem in computer science. Even today, after 50 years, we still don't know the clear answer for that. So these kind of problems are hard in nature. Now, well, it is reasonable to ask the same question for a quantum computer, not in that sense, but in the sense that, can you classify the problems that get benefit from quantum computing? And honestly, I just mentioned that previous example not to show that this is as hard as the other one. I don't know how hard this problem is, but I think it's worth looking at for various reasons. First of all, it is a cool problem, mathematical problem, or theoretical computer science problem. The other reason is that if you can tell me that this class of problems, you cannot really get anything by working on quantum side of it, then I won't waste my time by searching for a quantum algorithm for those things. So it's an important thing to know what kind of problems we can solve with a quantum computer. But this doesn't have a clear answer. Even the ones that, so we know that you need to have a structure in the problem so that quantum computing gives you something exponentially faster. But it's not easy to say exactly what is that point in the structure that you will use. There are various things that may help you. I don't have time to get into those things, but one of the main things is probably interference of different computational paths in a quantum computer, and which I won't get to talk about, but that's one of the main things you want to point when you're dealing with quantum computing. But instead of talking about these things, let's go and see what is going on in quantum computation. So first of all, I need to introduce some basic notations. So I'm going to talk about bracket notation, which is basically Dirac notation for vectors. So a ket is actually this one, and this just denotes a vector phi. And bra is this one, and it is denoting the dual of phi. So it's just the notation for vector. So ket is just a vector. And so at this point, when I say that ket is just a vector, then you may ask me, okay, why are you using this? We have everything ready in linear algebra for a long, long time. So why are you using this weird notation? So there are two reasons I'm using it. One reason is for this talk because I want to be consistent with the literature, as if you want to go and read more in the literature, you will see these notations, and I wanted to be consistent with that. But there's another reason. Soon you'll see that we will need to talk about Hilbert spaces of high dimensions, say 2 to the n. And if you really want to write vectors there for computations, even if you use row vectors, then you need a huge amount of space to write the things. Using Dirac notation and some conventions, you can turn it into a compact version of writing vectors and operators. So I'm going to talk about the same notation. I'll use the same notation. So if you're in a Hilbert space, then this bracket notation is the inner product of two vectors psi and phi. And we also use the following notation when you write a ket phi psi, it means really the tensor product of these two vectors. So for example, when I write 0, 1, then it is nothing but 0 transferred by 1. And what is this 0 and 1? It is written here. So, so if you want to deal with a qubit, then you have to talk about a two-dimensional Hilbert space. And in linear algebra and many places, so we just say standard basis when we are dealing with such bases. But in this case, in literature, they call it a computational basis. Okay, So now that we know what is a computational basis, which is 0 and 1, the question is, what is a qubit? Well, however you want to define information, at some point the information should be kept physically somewhere. And of course, the smallest place that you can keep information in a computer is a bit. And now here you're talking about a qubit. So what is a qubit and what are the states of a quantum system will be discussed here very briefly. And so let's take a look first at the classical bit. If you have a classical bit, you can only store 0 or 1. So your states is either 0 or 1, and that's it. But in a quantum bit, or a qubit for short, then it takes the states 0, 1, as I defined them in the previous slide. And it may also get a linear complex combination of these two things, which is called a superposition. So the coefficients are complex, and you have this relation. So I'm talking about a unit vector in a Hilbert space. So, and if you want to know this value, square of the absolute value or magnitude of C0 is giving you the, if you really measure your qubit and you want to know in which state it is, so this value here is probability of finding your qubit in state 0, and this one is the probability of finding your qubit in state 1. Okay, so we have more options than 0 and 1. You can have a superposition, or basically a linear combination of these two states in a qubit. So, but formally, if you want to talk about that in mathematical sense, the states, the space of all states for a qubit is modeled by a Hilbert space, complex two-dimensional Hilbert space written here. So this is the, and your states will become unit vectors there. Okay, now that we know what is qubit and how we keep information there, we want to talk about time evolution of a closed system. So you want to know how over time you do operations and stuff like that. And this time evolution, well, first of all, let me tell you what is closed system. By a closed system, we mean that your system, quantum system, is not interacting with its environment. So even for observing, it is assumed to be interaction. So at that point, we call it closed if you're not even observing it. So the time evolution of a state of a closed quantum system is described using unitary operators. As you can see, we are getting more and more into linear algebra. And a unitary operator, I think, on a single qubit is usually called a one qubit gate or a quantum gate. So when you hear quantum gate, it means that you are doing some operation on a bit or a system. And but notice that not all operations are unitary. For example, observing this state of the system is not unitary, but I don't want to get into that because we don't need it. Okay, so, but then you ask me, well, it seems that we have one qubit available in the world somewhere, right? And the answer is yes, we do have one qubit available. And then your next question will be, so if you have one, what is the problem of having many more of those? Can't we make copies of that? Well, the answer is yes, we can do that. We can have many of these qubits. But the point of having quantum computer is not just in having one single qubit or a bunch of qubits which are working isolated. The point is when they interact with each other. And then this is the time when you have to talk about composite systems, because it consists of n qubits where you have interaction between these qubits. And there you will see the power of quantum computers a little bit. So if you have n of these qubits which are interacting with each other, then the state of this space of the state space for this n qubits is presented by the tensor product of the Hilbert space I talked about to itself n times. And as we know, the dimension of such a space is 2 to the n. So we are talking, if you have n qubits, we are talking about 2 to the n coefficients. So if you have n qubits, what it represents 2 to the n complex numbers as coefficients of vectors in the as coefficients of the basis vectors. So what do we see here? We see that if you have n bits, you just have n bits of information. But if you want to compare the information stored or somehow presented using n qubits, this contains 2 to the n complex numbers. So it is exponentially containing much more information in comparison to n bits. And if you want to know, this is not the only source of advantage for quantum computing. There are other things I have to talk about, which is irrelevant to us for now, as interference and also entanglement of the system. So these are the things that I can't talk about because I don't have time for that. So I'll skip these things. But if you want to really understand the power of quantum computing, it's not just about qubits and composite systems. And the only thing I want to mention at the end here is that you don't have to, well, based on quantum physics, you don't necessarily end up in a finite dimensional Hilbert space. It works over infinite dimensional ones as well. But I don't want to get into that details because I want to keep everything simple here. Okay, that's almost all I needed to tell you about quantum computing. I know it was very brief, but it's not a talk on quantum computing. Let's get back to our business, which was solving the class group problem. But before that, as I told you, this hidden subgroup problem comes handy in many algorithms. So I want to take a look at this one. So hidden subgroup. So if I give you, if you give me group G and the subgroup of that, and X is just a set, so it's not necessarily a group, it's just a set, we say that F hides H if it factors through G mod H. So basically what I want to say is that F is constant on cosets of H, and it will give you a distinct value for each coset. In this sense, F hides H. And what is the problem? The problem has input the group, and F will be given as an oracle. So maybe it's worth to tell you that a very nice example of this situation when F hides something is that X is a group as well, F is a homomorphism, and if you consider the kernel of F, F is hiding the kernel. You can see the properties there. But this F is given usually as an oracle, by means of an oracle, and the size of the oracle is big O of the log of the size of the group plus the log of the size of X. So giving that as an oracle, the question is, can you determine what is H? Can you give me a generating set for H? That's the hidden subgroup problem. Now, before getting into results of what do we know for solutions, I want to point out the fact that this is a very important problem in many different problems, because you can reduce integer factorization to an instance of hidden subgroup problem. This is done by Shor and solve the problem. Also, discrete log problem can be translated into HSP. And also, shortest vector problem in a lattice can be actually reduced to computing hidden subgroup problem instance where your group is actually a dihedral group. And graph isomorphism problem can be reduced to the same problem where G is just symmetric group on n elements. So as you can see, if we have solution to hidden subgroup problem, then it might come handy easily in other places, which are important. But let's get quickly to the results on hidden subgroup problem. So when G is abelian, we know the answer by works of Shor, mostly, and Simon. And in the G abelian case, we can solve the problem efficiently. And if G is finite and H is normal in G, then Hallgren, Russell, and Tashema, they provide an algorithm which solves the problem efficiently.
I mean, to say you solve the problem means what? You discover the generators or the presentation?
No, we'll find a generating set for H.
Okay. And relations to?
Yes. And when G is finite and H is normal, you can do the same thing. And and when G is almost abelian, Grigny, Shulman, Vazirani, and Vazirani provided an efficient algorithm again. This works. If G is two-step nilpotent, then you can see that as a class of nilpotent groups. This is done by Ivaniush, Selsalm, and Santa, and this can be done efficiently for these kind of groups. And Kuperberg and Regev, these two independently showed that if you have a group G as dihedral group, then the algorithm they provided is actually sub-exponential. And so we cannot still solve the problem efficiently in the case of the dihedral group. And I also want to mention that in the case of the symmetric group, we don't have anything which is efficient or even close to efficient. So the case symmetric group is open. And also recently, Cooperberg showed that if you're working with rationals, and consider rationals and addition, then it will be NP-hard. So with this brief information on hidden subgroup problem, let me get to a specific case of that, which is important for our purposes. As the problem we are dealing with will be reduced to a hidden subgroup problem, but as it gets into lattices and they are in R to the M, then the continuous space will cause that you cannot easily work with the previous known algorithms, and it needs specific attention. And so for this reason, Eisentrager, Hallgren, Kitaev, and Song gave a definition of a variation of hidden subgroup problem, which is called continuous hidden subgroup problem. And this is basically the definition I'm presenting here. So your H in this case is a lattice, and your G is Rm. So you'll be given, you know that you're talking about your hidden subgroup will be some lattice, and you're working in G as Rm, and you know that L is a full rank lattice. And oracle for F will have some parameters A, R, and epsilon, and F is the one which is hiding your subgroup L, and here X is denoted by S, as this map is really encoding of R to the M to quantum states. So S is replacing is actually the X in the previous definition. And of course, it is unit vectors in a Hilbert space. As I said, this is the space of quantum states. Okay, now F hides L in the following way. So the first thing is that F is periodic on L. So if you have X in Rm and V in L, F of X is equal to F of X plus V. The other fact is it satisfies Lipschitz condition. And so if X and Y are close to each other, then it means that the quantum encodings of X and Y, which is written as using the ket notation, these two states will be close to each other as well. And the final property is the fact that is that if X and Y are not close to the lattice, then the states that they'll get are almost orthogonal. So these are the properties they defined, and of course you're free to define other properties, but these are the ones they needed to solve it efficiently, and they actually provide an algorithm which solves an instance of such problem in polynomial time. And this is what we will use in future soon. Okay, let's say what is S units group. So assume S is a set of prime ideals of an order in K. And then, of course, we consider all alphas in your field so that the ideal generated by alpha is actually can be written as a product of such product. And this is called the S unit group. This is basically generalization of units. And if you assume your S is empty set, then you'll get unit groups. But well, it is an interesting object because computationally, you can reduce class group problem to computing S units. You can also reduce principal ideal problem, which is basically given an ideal. Then the question is, can you tell me if it is principal? And if it is principal, can you tell me what is generator of this ideal? And you can also reduce norm equation solving to S units. And there are more actually. You can think about solving. You can actually think of computing Ray class groups, and probably other things can be reduced to S unit computation. And this S units is exactly needed where we wanted to give speed ups for that step of choosing relations. As you can see, the guys here, the equations here are actually very similar to what we have seen when we were talking about computing the kernel in one of the earlier slides. Okay, now let's get back to the reduction, which I said I'll tell you more about that. So now we want to reduce computing class groups to computing S units. So by a result of Bach, which is a famous one, and I told you that he provided a bound, and the bound is written here. And delta is actually discriminant of your field. And what you want to do, you can use this result to get B, a generating set under generalized Riemann hypothesis for your class group. And the size of this P is polynomial in terms of log of the discriminant, which is good. So it's not like a huge one as Minkowski will provide one. And it's not trivial to say that you'll have this, you can quickly get B easily, but believe me, there are polynomial algorithms that can compute B based on the result I've stated here. So if you want, you can take a look in paper by Biasse and Ficker from 2014, and there you'll find a section which actually gives you an algorithm, concrete algorithm, which produces this B in polynomial time. But having this in hand, then how do you reduce class group problem to S-unit computation? Well, it's more or less what we were talking about in the beginning of the talk, which was about classical algorithms. So what you say is that you put S to be the same B you have here. And so basically, this is a generating set for your class group. And then you say that compute the set of generators of S units. That's why it is a reduction to S unit problem. And then once you have this, this is basically a replacement for finding relations, choosing relations. Remember, so this gives you relations you want. And then form a matrix, and the rows will be formed, as I mentioned earlier. But these are basically evaluations of elements you can find in S at PIs. And then you will compute a Smith normal form of M, which is not really costly in comparison to other steps. And that's, name it H. And then if you look at the diagonal entries of H, that will give you a structure of the class group. But the only point you don't know how to do is this part, because it says that compute a set of generators for S units. That's why we call it, this is a reduction to S units. Now I have to tell you how you can find a generating set for S unit group. Okay, so let's talk about this part where you want to reduce S units computation to hidden subgroup problem. So as you can see, I have two sides of my screen. So it is on one side, you see the result from Eisentrager, Hallgren, Kitaev, and Song. The other side is Biasse and Song. As you can see, they're very similar and closely related. And this one is just for computing the unit group, and this one is just computing class group, and also it is in some sense used for computing principal ideal, for dealing with principal ideal problem. So I'll explain this one first. So here, units are identified with a lattice. So this is a lattice in Rm. Units are identified with a lattice. And how is it done? You can embed, you can use canonical embeddings, which are real embeddings and complex embeddings of your field to get such thing. And once you have once you have identified your units as a lattice in Rm, for each point in the lattice, they will give you a lattice in R to the n. And this m is actually big O of n. Sorry, big O of n. Then for each point in the lattice, they'll provide a map which will produce a lattice itself. And then you have to encode lattices using the quantum map. And this C refers to classical, this Q refers to quantum. And this will become one of those things related to quantum computing. It will be translated to your quantum states. So what are the objects we want to know? So remember, in a hidden subgroup problem, you had a G. In this case, it is R to the n. And you had H. In this case, it becomes your lambda lattice. And of course, you had an F to become an instance of hidden subgroup problem. And F is actually composition of these two maps. Okay, and then they just call their efficient algorithm for solving an instance of continuous hidden subgroup problem. And on this side, on the right side, instead of identifying units in R to the m, S units, the group of S units is identified with the lattice lambda sub S here. You see that it's very close to that. Well, part of it's coming from the ideas that it was used before, but this part, which is Z to the S, is coming from those evaluations at PIs. And once you identify your S unit group here, then again, similar idea applies. So for each of the points in the lattice, we will form a lattice here in R to the n, and then of course you map them into quantum states. So again, in this case, G is R to the n tau. this, and H is this, and F will become composition of these two maps. And then the algorithm will be called. So of course, I didn't give you all details on what is happening in here and here or the above maps, but probably I'm running out of time, unfortunately. So it's better to focus on these two maps, which are quantum maps. I'm going to talk about these encodings instead. So in order to tell you what is FQ, this is a quantum encoding thing, and well, as it is really a quantum computer, so a very nice question will be, you are talking about the quantum computer. So at some point, you should be able to encode whatever object you are talking about into quantum states. How do you do that? This is one of the main problems that in quantum computing should be addressed. And generally, it is not a trivial question. How do you encode objects into quantum states? But what you can do here, you can see one way of encoding your objects into quantum states, and these are specific objects, not general. So the first, the fact is we want to encode a lattice eventually, as you have seen in the previous slide. But encoding the lattice means that, well, you think you can use a basis of that, but the point is that a basis is not unique. So it's better to make sure. So you want to make sure that your encoding is unique. So you don't want to use a basis. You want to use lattice points. But in order to do so, you're dealing with vectors in Rn, so you need an encoding for vectors in Rn. So basically, for a vector in Rn, you want to see that in a grid, and then you want to use the lattice point around that, and then superposition of those points will become your state which you are looking for. But in concrete terms, let me first tell you how it works on one single real number x, and then we'll see a vector in Rn. So if you have x and you want to encode it into a quantum computer, what you can do, you can consider a grid and then say this is k plus 1, and your x is somewhere here. And then what you do, you find this k, and of course you know then what is k plus 1. So you're looking the closest grid points into your x, and then you name this part to be your t. And then what you do is you define such mapping. So x will be encoded to, it's using straddle encoding, into this state, which is basically a superposition of the state k and k plus 1. As we figured out, k and k plus 1 are those 2 points which are close, representative of those 2 points close. And then what are the coefficients? Of course, coefficients are real, but it is allowed to be real because we need complex coefficients. And they are designed in such a way that the closer x gets to k, this one gets larger, and the closer gets x to the other point, this one gets larger. And as you can see, this is a unit vector, and this is an encoding for into quantum states. So it's a superposition of two states. So now you can actually encode a real number x. Now, once you have such thing in hand, the question is, how do you generalize it to a vector in Rn? And that's not something hard. As I said, it's similar of thinking of that in if you have a point, if you have a vector in R to the n, and what you want to do is that you want to see the grid around that, and the grid is relevant to your parameter delta, of course, and you see the points around that vector and that point in the space, and then you consider superposition between all those points, superposition of all those points with the fact that you have some coefficients which is coming from encoding of one single real number. So in mathematical terms, what you can say is that you can encode a real vector into quantum state using the tensor product of the component-wise encodings of components of your vector V. Okay, now you have this thing in hand. You can talk about the encoding FQ. So we have a map here. I don't want to get into that. I'm really running out of time. So you have this for coefficients, and there's a weight here. There's some constant here you're working with. But apart from that, what you do once you know how to encode, once you know how to encode a real a point in real space, then what you do is you can easily consider superposition of all those points in the lattice. So how do you encode the lattice? It is just considered with, of course, some coefficients and a constant here, but it is basically a superposition of all points in your lattice, and that will give you a quantum state. So you could really encode your lattice, and this is the second map, actually, F sub q, which I was talking about in the previous slide. And this completes the information on providing, reducing the S-unit group computation to computing a hidden subgroup problem. But this was a lot of information. Let's just summarize this thing. So assuming, I have a couple of minutes, right?
Yes, you do.
Okay, so assuming generalized Riemann hypothesis, there exists an efficient algorithm for computing the class group. And where do we need this generalized Riemann hypothesis? This is exactly where you wanted to find this instant of S set. If you don't want to assume generalized Riemann hypothesis, then, well, you still can do that using Minkowski's bound, but I'm not aware of any other way other than GRH that will provide S in polynomial time. So eventually, if you don't use that, you will end up with an exponential complexity, even if you use this quantum algorithm, because that part is a classical reduction. So, so the first part was given as a classical reduction here. And then the second part was a quantum reduction, which is basically translate the problem of finding S units into a continuous hidden subgroup problem instance. And eventually, you can solve that using an algorithm by Eisenträger, Hallgren, Kitaev, and Song. So this basically gives us what we wanted. But just to mention the fact that you can replace this thing, class group computation, with principal ideal problem. And in that case, you will get another specific type of S. And in that case, unfortunately, you'll need to use factorization, because I will give you an ideal. I will ask for a generator for that if it is principal, and if it's principal, give me a generator. And in that case, if I give you the ideal, then you want to really decompose the ideal or factor the ideal. It means that you're using a factorization algorithm. So this part, if you want a polynomial time algorithm, this part cannot be classical, because the best you have is sub-exponential. But if you are willing to do that in quantum sense, which eventually you are doing that, then we have, well, quantum factorization algorithms which are efficient. So you can do that. The principal ideal problem can be solved. And also, you can use the same idea on norm equations, solving norm equations, and possibly more, such as other things in number theory. But that was all I wanted to talk about. And sorry for being fast at some points. I was running out of time.